Okay, so we're going to look at the multiplication rule, and here's how we're going to do it. I'm just going to give you one example that you're familiar with, and I'm going to show you where it appears in a tree diagram, and then try to envision how you would create a tree diagram for all of the problems in these sections. So let's start off with, we have two events. E is the event, maybe I'll just define it. Let's say H is the event of flipping a head when you flip one coin. Then we can write the probability of H, the probability that you would get a head. And we've calculated this before. There's one head of the two outcomes. And let's let, well, let's say 3 equal the event of rolling a 3 when you roll one die. And we know that the probability of rolling a 3 is 1/6, because there are 6 different numbers that can come up. They're all equally likely. Probability of getting a 3 would be 1 in the total number of outcomes 6, 1 in 6. Now, the question that we're going to ask today is, what is the probability that both of those things will happen? It's sometimes convenient to talk about, the two things happening at the same time. So the big problem that we're going to ask today is, what is the probability that both of those two things will happen? That is, you either take the coin and flip it and then roll the die and record the outcomes, or you just take them both in your hand and just give them a toss and then record what they have on there. So what's the probability that a head and a 3 will come up? And this word here, and, is different than what we worked on before, because in the previous section we looked at the probability of E or F, and today it's going to be E and F. And there are two formulas that'll help us calculate that. And they're both called the multiplication rule. So the addition rule was for E or F, the multiplication rule is for E and F. But I'm not going to use the formula here. What I'm going to do is just write down all the outcomes. So you can have a head and a 1, a head and a 2, a head and a 3, a head and a 4, a head and a 5, a head and a 6. Those are 6 different outcomes. Or you can have a tail with each of the 6 rolls of the die. And this would be the sample space. And we would write it that way. So the number in the sample space is 12. How many of those 12 outcomes do we have both an H, a head, and a 3? How many of them? Well, no, we can't count that one because that's a head, but it's a 1. Can't count that one. Oh, there's the one we want, a head and a 3. There are no other heads and 3s. So there's only one outcome in that entire 12. There's just one. So the probability of head and 3 would be that one outcome divided by the 12 possibilities. So it's 1 in 12. Now we can calculate this using just knowing all the outcomes, using the simple definition of a probability. Number of ways the event can occur divided by the number of possible outcomes. And it's 12. Now I want to show you the multiplication rule and how it works. And the first thing we have to talk about is independence. And independence means, does the probability on one of the events somehow, if you knew the outcome, would it change the probability of the other one? In this context, we would say, we know that the probability of getting a 3 is 1/6. But what if we flipped the coin first and the coin came up heads? Would that change the probability of getting a 3 on the roll of the die? I mean, does the probability of rolling a 3, does it change from 1/6 to something else? And the answer is, thank you, Shay, no, it doesn't. The probability of getting a 3 is always going to be 1 in 6. So the outcome of the coin does not influence the probability of getting a 3. When that happens, we say that those two events, flipping a coin and rolling a die, are independent. One does not influence the other. So we would say H and 3 are independent. Knowledge of what you, the roll that you get on the die does not change if you know the outcome of the of the coin toss. All right, now I'm going to introduce, okay, so this is important. Now I'm going to introduce a tree diagram. And let's say that even though I ask you this probability in terms of what's the probability that they both would have happened, get a head, get a 3. So we can do it this way. First of all, even though I didn't say that they were done in sequence where we flip the head first and then or flip the coin first and then roll the die, it's useful sometimes to actually do those in order and think about doing them in sequence where you first flip the coin and then you roll the die. So for the coin, we can get a head or a tail. And what we're going to do is we're going to write the probabilities of getting a head or getting a tail on the branches. Call these the branches, coin. And then we're going to roll the die. And I'm only interested in getting a 3 or something else, not a 3. We can get a 3 after we flip a head, or we could get a 3 or not a 3 after we flip a tail. So I want to make sure that my tree diagram has all the possible outcomes here. We also know that the probability of getting a 3 is 1/6, and the probability of getting something else, not a 3, would be 5/6, same down here. And then focus in on these two numbers here. Do those two numbers change depending upon what occurred beforehand? Do these probabilities, are they different if you get a head first versus a tail first? No, they didn't. They're the same exact thing. If this happens, we know that the two events are independent. The probability of getting a 3 after you flip a coin is the same whether you get a head or a tail. So that's the idea of independence. Now, if you can create this tree diagram, then here's how you calculate the probability. If you want head and 3, just follow the branching that goes from head and 3. And then the probability of head and 3, what we're going to do is just multiply the probabilities along that path. So the probabilities, if you go head and then 3, you have 1/2 times 1/6, and that is, no surprise, equal to the 1/12. So we showed it up here using the definition how to calculate it, but the tree diagram is much more powerful, and it'll calculate the same probabilities for you. And the two events don't even have to be independent for this to work. So if you can, try to draw a tree diagram when you have this and that probabilities. Here is the first rule. The probability of E and F is equal to, well, we just took the probability of E and then we multiplied it by the probability of F. But it only worked in this narrow setting. And it works if E and F are independent, like a coin toss and a die roll. This is the multiplication rule because it involves multiplication of complex events. Okay, so I should say, part one, because there are two parts to this. Now I want to give you an example of the second version. The tree diagram will work, but I need to talk about conditional probabilities. We're going to write it this way: the probability of E, then a vertical line, that means given, and then you have given that F has already occurred. So in our example, what's the probability of getting a 3 given that a head came up on the coin toss? And I'm going to write it out in words. So look for the word given, because chances are, if you see that word given, that it's going to reduce the denominator of that probability. We're going to say, instead of taking a random sample from all the groups, we might say, what's the probability that someone owns a dog given that they are female? Then we reduce from all individuals to females only. Now in a tree diagram, I'll just write F and F complement here, just so I have two different events. And then up here, E, and then E complement, something like this. All right, I want to share with you what we label on each one of these. This branch right here would be the probability of F, because we're going to F, and we put probabilities on the branches. This one down here is the probability of F complement. At every branching, we know that these two add up to 1. When you add the probability of F with the probability of F complement, it's going to equal 1. So at every branching, the two probabilities are going to add to 1. If you had 3 branches, then the 3 will add up to 1. All right, now, the way that we label these probabilities changes because we can't just write here the probability of E, even though we're going to E, because something has already happened. And what has happened is that F has occurred. When we're coming up this branch, F has occurred. So every probability after the first, all of these will be conditional probabilities because something has occurred before this. This first one is the probability of E because that's where we're going, but given that F has occurred, and we would write it that way. Now this one here, this is the probability, since we're going to E complement, it's the probability that E complement will occur given that F has occurred. So we write the vertical line and then F has occurred like that. And then as we come down this branch, this would be the probability of E, since that's where we're going, but F complement has already occurred. So given F complement. And finally, the probability of E complement, because that's where we're headed, given that F complement has already occurred. So all of these are conditional probabilities. But we calculate the probability of E and F in the same way that we did on that other example. So what we're going to do is we're going to follow the path, for E and F. By the way, the probability of E and F is always going to be the probability equal to the probability of F and E. So that can be useful sometimes. If you follow the branch F and E here, and you want to know what the probability of F and E are, just multiply the probabilities along the branches. The probability of F times the probability of E given F. It would look like that. All right, let me do an example so you can see what it would mean. By the way, this works for any two events. The two events do not need to be independent. They could be, but they don't need to be independent. All right, we'll do a cards example. So what is the probability that 2 hearts will be, you can think of it as being dealt to you in a 2-card hand, or you can think about it in terms of 2 random draws from a deck. And then I'm going to add this phrase without replacement. Because when you're being dealt hands in cards, you're dealt one hand or one card, and then that card is not placed back into the deck. Or what we're assuming here is that we're going to take one card out, and then before we're going to set that card aside. So the first card we're drawing is from 52 cards in the deck, and the next card we're going to draw, since that first card is not replaced, we're going to only be drawing from 51 cards. All right, so that's the difference. And maybe we'll do it with replacement as well, just so you could compare. Okay, so heart and heart. And here's what you need to know, that there are 52 cards and there are 13 hearts and 39 non-hearts. The 39 non-hearts are the clubs and the spades and the diamonds. All right, here's our tree diagram. The first card is going to be a heart or not a heart. And then the second card, so this first one is going to be without replacement, and the second one will be with replacement. The idea in the second version is that before we select the second card, we are going to replace the first card back into the deck, presumably shuffle up the cards, and then select the next card from the full 52 card deck. All right, so heart, not a heart, heart, not a heart. So this represents the full experiment of drawing 2 cards out of the deck, where your intent is to decide whether you, or to calculate the probability that you get 2 hearts. If we do replacement, well, that doesn't change the tree diagram at all, at least the initial part of it. Okay, so let's go through each of these scenarios, see where they're different, and then talk about independence. All right, so the first draw, think about just taking that first deck. What's the probability of getting a heart? Well, there are 13 hearts and 52 cards when we make that first draw. So we would say the probability of getting a heart is 13 out of 52. Now, I know that you can reduce that fraction. You can if you want, but I'm not going to reduce it yet. And the probability of getting something else would be the probability of getting a diamond or a spade or a club. And there are 13 cards in each suit, so 13, 13, and 13 would be the 39. And it turns out your first draw over here with replacement, you know, these are the same because in the experiment, we're drawing the first card from a 52 card deck. So it makes sense that the probabilities would be the same. Okay, when we get into the next round, let's do with replacement first, because this is the easier one. If we took the first card and we looked at it and recorded it as the 7 of hearts, or we recorded it as the 2 of spades. Anyway, we recorded what the card was, and then we took the card and stuck it back into the deck, shuffled the deck, and then drew our second card. So here we are. What's the probability of getting a heart from that new deck? Okay, so give me your answer in the chat. All right, so we're right here. This is the one we're trying to calculate. Let me say it again. This is with replacement. We drew the first card. It could be a heart or it could be something else. We calculated the probabilities here that you would get a heart or something else. We took that card and we stuck it back into the deck. We replaced it with replacement. We replaced the card back in the deck, and now we want to calculate the probability of getting a heart in that second deck that also contains 52 cards. Right, since we replaced the card, the probability is exactly the same, 13 out of 52 and 39 out of 52. It's like two draws from two different decks that contain 52 cards. The same thing down here, 13 out of 52, and then 39 out of 52. And so you'll notice that these two probabilities are the same. They do not change because of knowledge of what came first. So here we could have had the ace of hearts, but we put it back into the deck. So the probability of getting a heart on the second draw is still 13 out of 52. Whether we get a heart, ace of hearts, or whether we get a 2 of spades. We're taking the card and putting it back in. These probabilities do not change. So knowledge of what we got on the first card does not change the probability of getting a heart on the second card. We say that the two events are independent in this case. And that was similar to our previous example, where these two probabilities did not change. All right, now we're going to go over to the other one. In the first one, we're going to select the second card after we know that what was selected on the first card. So if we're coming up this branch, we know that, say, an ace of hearts was selected. So what's the probability that the second card is a heart? If we knew that the ace of spades is sitting on the table, ace of hearts, excuse me, because we know we drew a heart. So there's one fewer heart in the deck and there's one fewer card in the deck. So what's the probability on the second card, if we don't replace the first one, of getting a heart? Okay, see some good answers there. There are only 12 hearts remaining because we selected the ace of hearts because we're coming up this branch. Didn't have to be the ace of hearts, could have been 7 of hearts and 6 of hearts. And there's one fewer card, 51. But there are still 39 non-hearts. And notice that in every branching, these two probabilities add up to 1. No matter where you are, anywhere. These add up to 1, these add up to 1, and so on. All right, now, you can't just take these probabilities and move them down here. Here you could because the two events are independent. So we have to go back and think differently. Now let's suppose we're coming down this branch and the first card we selected was a non-heart. So let's say it was that 2 of spades. So now we're sitting and we're going to draw the second card. We still have 12 hearts, but we have one fewer non-heart in the deck, and we only have 51 cards in the deck. So on that second draw, what's the probability of getting a heart? Okay, 0. Okay, so in the second, after we take out that 2 of spades, there are 51 cards remaining, and since the first card we drew was a non-heart, there are still 13 hearts remaining in the deck. But there are one fewer non-heart, so that would be 38 out of 51. And this is the way that we define a tree diagram and label the trees with probabilities, the branches with probabilities. Now notice that the probability of getting a heart on the second card changes. So knowledge of what we got first, whether we got a heart first or whether we got a non-heart first, it changes the probability of getting a heart on the second draw. If this happens, we would say that the two events are not independent. And I'll just calculate the probabilities, and you can see that they are slightly different. In the first one, the probability of a heart and a heart, you're going to multiply the probabilities along the heart-heart branch. And so you have 13 over 52 times 12 over 51. And then you can simplify that. Over here, if you have with replacement, then it's going to be 13 out of 52 times 13 out of 52. And that one I do know. This is 1/16. And this one here is 1/17. And it reduces. So they're very similar, yet different. So please consider tree diagrams in this section. There's one other formula I want to give, and it comes from this. This is the called the general multiplication rule. Earlier I said multiplication rule part 1, so maybe I'll call this multiplication rule part 2. But what the beauty about this part 2 formula is that it works for any two events. And those two probabilities that you multiply together will appear on a tree diagram. Okay, so conditional probability rule is really not a new formula. It's just this formula, but instead of solving for probability of A, E, and F, we're going to solve for this one. Because the one that I circled there, that's the conditional probability. So the probability of E given F is equal to, well, what you could do, both sides of this equal sign, is just divide by the probability of F. And then those would cancel. So you get the probability of E given F is equal to the probability of E and F divided by the probability of F. Okay, now you got kind of an overview. You got the formulas, and those are all the formulas from both of those two sections, 5.3 and 5.4. So what I'd like to do now is to go ahead and calculate, or actually go through a lot of problems so you can see how these things, the tools that we're going to have to do these problems are the formulas and the tree diagram. So consider those two. And I'll also do a Venn diagram later as well. Okay, the first problem is go through number 7 and decide whether those two events are independent or dependent. Does knowledge of one change the probability of the other? So A, B, C, D, right? Dependent or independent? Okay, so these examples are not, coins and dice, but dependent, independent, independent. Okay, so some of you are putting answers in there. Okay, so you can ask the question this way. If you knew that someone was speeding, would they be equally likely to be pulled over by a police officer? Would they be less likely to be pulled over by a police officer, or would they be more likely to be pulled over by a police officer? And let's just make it extreme. Let's say someone's driving 100 miles an hour down the highway, and then there's a police officer sitting in the median. Also, now let's consider that someone's driving 65 miles an hour in a 65 miles, so going the speed limit, and passes that same cop. Does knowledge of whether the driver is speeding or not, does that change the probability of whether they'll be pulled over or not? Does it change the probability? It does. So you're more likely to be pulled over if you're speeding than if you're not speeding. So we would say that these are not independent, or you could say dependent. In the next one, gaining weight and eating fast food. Well, eating fast food or eating out in general, when you tend to eat out, you tend to consume 2 to 3 times as many calories as if you just prepare food yourself. So whether it's fast food or something else, most of the time when you go out to eat, you consume more. You might have a drink, a high caloric drink or something like that. So if you knew someone went out to eat every night at a fast food restaurant, and then you have this other person who prepares their own food and does not go out to eat every night, would the probability that they gain weight differ if you knew that they were going out to eat every night? Would it be more likely that they gain weight? And the answer is yes. So yeah, I mean, if someone goes out to eat every night, the probability that they gain weight is probably closer to 1. Whereas if they don't go out to eat every night, if those are the only two things you're considering, everything else being equal, then if they don't go out to eat every night, then the probability of gaining weight is probably lower. So knowing whether they go out to eat every night or not changes whether they gain weight or not. So here's another one where it's not independent. And the third one, let's say that you get your test back and you score 90. All right, well, let's say that instead you get your test back and you score 30%. Does knowledge what you got on that test exam, a 90 versus a 30, and then you go watch baseball at night. Does your exam score, is it going to influence whether it's high or low? Is it going to influence whether the Boston Red Sox win a game or not? No, whether the Boston Red Sox win or not is independent of how you score on the exam. There's no connection whatsoever. So we would say that these two events are independent. Okay, continuing through, we got lots of problems to go through, and you'll see these similar problems tonight. Suppose that the two events are independent. Now, normally in problems, you're going to have to figure out if the two events are independent or not. But here they tell you that they are. So if the two events are independent, then here's the version of the multiplication rule that we use. The probability of E and F is equal to the probability of E times the probability of F. Now let me give you a caution here. So you just take the probability of E and then you multiply it by the probability of F. Get your calculator out and calculate that. Please don't stop reading this section here. Many students, when they're learning probability for the first time and they see the probability of E and F, they're just going to multiply these two. 95% of the time, if you do that, you'll be wrong. Because in most cases, the two events are not independent. But in this case, they told us they were. All right, here's your answer. Let's multiply the two probabilities. Let's multiply along the branch. Okay, next one, audits and pet ownership. Okay, your tax return can get audited, but that only happens to 6.42% of Americans. Do they get their tax return audited? We know our president is one of them, talks about it a lot. According to the Humane Society, 39% of all households own a dog. I think we did an example earlier where it was 30-some percent. Assuming dog ownership and audits are independent. So if they're independent, then we can use this version. So the probability of you get an audit and you own a dog, since those two are independent, we can just take the probability that you get audited and multiply that by the probability that you would own a dog. Because it says independence, we can apply this rule. The probability that you're audited. All right, well, we do have to convert that to a decimal, and we have to convert 39% also to a decimal. So we just take those two numbers and multiply them together. Okay, so this multiplication rule works not only for just two events, but as long as all of the outcomes are independent, then you can just multiply more events or probability of more events together. So just imagine that if you had a tree diagram where you had, E and F, and then E and F, and so on, and maybe there's another branching where you have E and F. The way that these, if all of these events are independent, all the E's are independent, if you wanted to calculate the probability of E and E and E, well, instead of just multiplying just two probabilities together, you may have three probabilities that you multiply together. Each of these is 1/4, and they're independent, so it doesn't matter what happens before. Then you could just take 1/4 times 1/4 times 1/4. The probability of E times the probability of E times the probability of E, right along the branch. So it's generalizable for more than just 2 events. You can have 3 events or 4 events or 5 events. That's what this is saying down here. So if you have n independent events, you could just continue to multiply the probabilities together. Given that, and then given this next result, these at least probabilities, it works with the complement rule. So basically what this is saying here is that the probability of at least 1, and we'll do some problems where this actually is going to be used, is equal to 1 minus the probability of none. And this is the complement rule. The probability of F complement is equal to 1 minus the probability of F. It just so happens that at least 1 would be 1 or 2 or 3 or 4 or 5 up to the maximum number. The only outcome that it doesn't count is the 0 outcome. And since the probability, all the probabilities add up to 1, if you just exclude the 0 outcome, then 1 minus the 0 outcome would be the sum of all the others. And that's what this is saying. So let's see how it would work in a problem. All right, so you may be familiar with Christmas lights. And sometimes if just one of the bulbs burns out, then the entire string of lights go out. That's what they're talking about here. Christmas lights are often designed with a series circuit. This means that when one light burns out, the entire string goes black. Suppose that the lights are designed so that the probability that an individual bulb will last 2 years is equal to 0.995. So there's a very high chance that each individual bulb will last for 2 years. Problem is, we need all 100 lights on the string to work in order for this to, the whole string to still be working after 2 years. Okay, so the success or failure of a bulb is independent. So in this whole section 5.3, they're going to state that the events are independent. And in the next section, we're going to work on, well, what if they're not independent? Okay, so what is the probability in the string of light that all 100 will last 2 years? Since they're independent, the probability of the first will last 2 years is 0.995. The probability of the second is also 0.995 because those bulbs are independent. They're going to last 2 years or not, independent of what some other bulb does. So we're talking about individual bulbs. And then the third bulb, it has a probability of 0.995. And then dot, 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 the 100th bulb will also have a probability of 0.995. So we're calculating the probability that all bulbs will still be active after 2 years because that's the only way that the whole string will be active after 2 years. So when we know there is independence, we can apply this rule. And our n in this case is 100. So we're going to multiply 100 probabilities of this kind of 0.995. So part A, the probability that all still work after 2 years is equal to the probability that the first one lasts for 2 years and the probability that the second one lasts 2 years. And so what you're going to do is you're going to be multiplying this 0.995 times itself 100 times. And we have a shorthand notation for that in math. We use exponents. So we're going to get the calculator out and compute 0.995. And we'll use the caret symbol here to use big exponents. And you can see this is the probability, which is nice. I mean, after 2 years, there's only a 60% chance that the whole string will last, even though each individual light bulb will last with a probability of 0.995. All right, now I'm going to get into that at least one, because here you see it, at least one. So the probability of at least one burnt out is equal to, I'm going to frame it in terms of the at least one probability that we saw on the other sheet. The probability of at least one is 1 minus the probability of none. In this case, it means none burn out. So here's how you would write that at least one probability formula in this context. The probability that at least one burns out is equal to 1 minus the probability that none of them burn out. Well, it just so happens that we calculated the probability that none of them burn out in the previous problem. So we're just going to take 1 minus this number that we have right here. And that's going to give us 39423. All right, so these last two problems on this sheet, I'll write the answers to them. So, and if we have time, we'll come back to them. But I want to go on now to the next section, 5.4. Oh, by the way, COVID, this is important. You know, why is it that the CDC and the WHO, why do they say avoid large crowds? You know, it's not like they don't want you to have fun. In the state, in the city of, let's say you're in Saginaw, and we know that there are about 72 deaths per 100,000 in the population. Right now, they keep track of this. If you go to the CDC site and you look at county data, in the county of Saginaw, I believe the death rate is 72 deaths per 100,000. So if you take 72 and divide by 100,000, you get 0.00072. I'm going to move the decimal point 5 places, I guess. 1, 2, I think this is it. 72 divided by 100,000. 1, 2, 3, 4. Yeah, that's it. So that right there is the death rate in Saginaw. Now let's assume everybody in Saginaw has this percent chance, okay, so it's 0.072% chance of dying from COVID. Now let's say that you went to a bar and there were 100 people and they weren't practicing social distancing, they weren't masking up, let's say, because all of this would change, I suppose, if people were mitigating and trying to avoid the coronavirus. But this is it. So if we have 100 people, the probability that they would die from COVID is 0.00072. But if everybody, each of those 100 people in that bar have this probability, we would have 0.0072 to the 100th power. It's not quite that. So I have to switch things around. So this is the probability of having COVID. So if you subtract 1 from that, there's a 99.928% chance of not having COVID. So it's not this one. It's 0.99928 to the 100th. So just like our previous problem, this would be the probability that none of the folks that are attending that bar has, because everyone has only a very small chance of having COVID, so the chance that they don't have COVID is here. So then we can calculate the probability that at least one person at the bar has COVID. And using the same thing that we did in the previous example, here's the probability that none of them will. So we take 1 minus the probability that none of them will, and we can calculate that. And there you see it. There's a 6.9% chance that at least one person will be there. Now it's a low chance, so in the city of Saginaw, you still could go to a bar and you would be unlikely to get COVID. But if you go to that same bar, or maybe it's a wedding, and there are 300 people, let me change this probability to 300. Then there's a 19% chance. And the larger the crowd, like let's say you go to the Lions game and they have 30,000 people there. Well, If they have 30,000 people, then the probability that someone is infected is essentially a certainty. It's 1. So this is why the recommendations from the CDC is to avoid large crowds. If people would just avoid large crowds and wear masks, then we could have this COVID thing taken out. As it is now, since we're not doing anything, they're predicting 400,000 deaths by the end of the year. Okay, let's take a look at some of the problems. Again, I gave you all of the formulas and the tree diagrams that are going to help you with these problems. I've already given them to you. So you see those 2 formulas up here. So let's go through and work through some of these problems that appear underneath. So here's one here. This is another one of those, just like you started your group work today, where I gave you some things that look like this, where they have the P of this and P of that, and gave you some numbers for them. Whenever you see something like this, then try to use a formula. And for this one, it's the conditional probability formula. So here it is. And let me go back to it to kind of refresh your memory. There it is. So I wrote down this formula, and this is the one that we're going to use. The probability of E given F. Now, if you happen to see the formula where the E and the F are switched, the top part is still the same because the probability of E and F is equal to the probability of F and E, but the what is given piece, that's what appears, the probability of it is what appears in the denominator. So when you have all these formulas, this is the probability of E and F divided by the probability of E. So this is our formula. They want to know what the probability of F given E is. So from the problem, we know that the probability of E and F is 0.21. So we're going to insert that numerical value in place of the probability of E and F. And then the denominator is the probability of E. And they also gave that number to us to be 0.4. So you just punch that on your calculator and you get 0.525. So the formula is one of the tools that you can use to do these conditional probability formulas. They also give you one that uses, it's like an empirical formula where it uses numbers instead of probabilities. And that one appears up here as well. So instead of using the probability of E and F divided by the probability of E, we could just use the number of outcomes in E and F and divide by the number of outcomes in E. So this one would be the number in E and F divided by the number in E. And the reason we're going to use this version is because of what they gave us in the problem. So 380 on top, and the number in E on the bottom. And then we're just going to get the calculator out to, we can convert it to a reduced fraction, or we can just round it to 3 decimal places. And this one here, it's the same thing, but we're going to use the general multiplication rule. All right, so if we were just using the multiplication rule for the probability of E and F, and we knew the 2 events were independent, then we could stop right here. The probability of E and F is the probability of E times the probability of F. But if we don't know the 2 events are equal, then we have to use the general multiplication rule. And that's good because they give us the probability of E and they give us the probability of F given E. So just multiply those 2 numbers together. Okay, you'll be asked frequently if to confirm that 2 events are independent or not. And here is the test on this one here. Here's if the 2 events are independent. So we have 2 versions of the general power rule. We have this one. This is the general power rule. And here's the other one. This one only works if E and F are independent. So I've given you those before earlier in this session. But notice that they only differ here. Everything else is the same. So another way to think about this is that if E and F are independent, then this formula works. But this formula works all the time. And so if E and F are independent, then these 2 things have to be equal. So this leads us to the test for independence. Early on, I ask you questions like, are these two events independent? You're speeding, get pulled over by a cop. It's kind of in a more applied setting. In this case, we're going to determine if two events are independent using a formula. And the formula is this. Two events, E and F, are independent if the probability of F given E is equal to the probability of F. That is, these two things are equal. If this one is equal to the probability of F, then you just have this formula here, and we know that this formula works if E and F are independent. So in some of the problems, they're going to ask you, are these two events independent? And here's what you check. If you have equality, the two events are independent. If you don't have equality, then the two events are not independent, dependent. All right, so let's look at a couple of examples here, some applied examples. Cause of death. According to the United States National Center for Health Statistics, 0.15% of deaths in the US are to young people between the ages of 25 and 34, whose cause of death is cancer. In addition, 1.71% of all those who die are 25 to 34 years old. And then it says, what is the probability that a randomly selected death is the result of cancer if the individual is known to have been in that age range from 25 to 34 years old? So, you know, if is another word that we use to signal conditional probabilities. Given is the one that you're going to see a lot. So we have two events here. One is that the age is in the range from 25 to 34. And the other one is person dies of cancer. So let's go back and after I've read it the first time, I have a sense of what the events are. And now we're going to go back and read it using these two events. According to the National Center for Health Statistics, 0.15 deaths are to those folks whose cause of death is cancer. So the probability that the age is 25 to 34 and the person dies of cancer, F, is equal to 0.15%, or 0.0015. All right, we have to always use decimals and not percentages. So that was the first probability that they gave you in the problem. You have to translate the words into symbols. In addition, 1.71% of all those who die, okay, so the probability of E is equal to 1.71%, and we'll convert that to a decimal as well. And I guess we're out of time, so let me just finish up this one. The probability that they're asking for that is the result of cancer, person dies of cancer, F, given that the individual is known to be 35 years or younger. So it's just a matter of picking the pieces out, and then we have the probability of E and F on the top. We're just going to write down the formula divided by the probability of E, and those two probabilities are exactly the two that they gave us in the problem. So you get your calculator out and divide those two numbers, and the result is the answer to the problem.